Okay, so this is just a short introductory video introducing the fluid tube manometer. So the fluid tube manometer is going to be used in many of the experiments in the energy systems and thermofluids module. Okay, so the fluid tube manometer, what you have is a series of tubes filled with fluid, and these are all connected to a reservoir of fluid at the back. Now in this case, this particular model here, the fluid in question is water with just a dye in it to help visualize it or help to see the fluid. So what you have is a reservoir of fluid with a line leading down to a manifold at the bottom, and then all of these tubes here are connected to that reservoir. So at the moment this is connected to a flow around a bend apparatus, but the apparatus is not running, so everything is just at atmospheric pressure. So what you'll find is that, let's say these tubes on the left hand side here, these are all open to the atmospheric pressure. So you have atmospheric pressure from the room is pushing down through this open tube at the top. So the fluid inside has reached a level, and essentially that level it's at the same height as the level of the reservoir back here. Okay, so those would be at the same height there. Now what would happen if you were to introduce a positive pressure? If you were to introduce a positive pressure into this port at the top here, that positive pressure would push down on the fluid here, and if it was above atmospheric pressure, it would push the fluid down the tube. Okay, until such time as it reaches a level where the pressure pushing down on that fluid was equal to the pressure, atmospheric pressure pushing down on the reservoir at the back. Similarly, if you were to introduce a negative or a pressure below atmospheric pressure, essentially what would happen is the negative pressure here would suck liquid up the tube until such time as it reaches an equilibrium with the atmospheric pressure pushing down on the reservoir. I'll show an example of that in action in just a moment. Okay, so what you can do is, in each case, you can measure the height of the column of liquid, or water in this case, off the scale. So if you take your eye down level with this here, you can read that tube there at the moment is open to atmospheric pressure, and that's reading at about 300 millimeters. Okay. Now the actual value of that doesn't particularly matter, but what matters is, say that 300 millimeters there, that's currently the height of the fluid in the reservoir. Now if we apply a positive pressure to that tube, let's say that fluid would be pushed downwards to 260 millimeters. It's the difference in those between the 300 millimeters that the reservoir is at compared to the 260 that the pressure that you're measuring is at. The difference in height of that column is what matters. Okay, now I'm just going to start this experiment here, and what we have is 4 tubes coming from a flow around the bend apparatus. So 4 tubes located radially across the section of the bend here. So we have a plenum chamber here that has a positive pressure inside it, so it's forcing air out through this apparatus here. And what we'll find is there'll be 4 different pressures at these 4 locations across the radius of the bend. Okay, so one at the innermost chamber, or one at the inside radius of the bend, and a second one, third one, and a fourth one. So 4 going radially outwards across the radius of the bend. And those are just literally connected. So you have pressures coming along these hoses here, and they're connected here. So this is 1, 2, 3, 4. So that's the innermost one on the radius to the outside radius. Okay, and I've an extra one here that's connected to the inside of the chamber, the plenum chamber. The second one here is just open to atmosphere, and the one over here to the left is open to atmosphere as well. So in each case, what I'm going to do is say, after I run the fans, I'm going to compare the tube that's open to atmosphere compared to the one on the inside radius of the bend. And I'll compare, say, the next one to the atmospheric pressure, and compare the next one to atmospheric pressure, and compare the next to atmospheric pressure. So in each case, what you're looking for is the difference in height between the pressurized column and the atmospheric pressure, or the one that's just open to atmosphere rather. So I'll just pause for a second and I'll set up the experiment. Okay, so there's a little bit of noise from the fan, so hopefully you can make this out, but we see here we have the plenum chamber. This one is just open to atmosphere, and then we have the 4 ports radially across the bend. And if we look down here at the manometer, you can see the level of the fluid in the chamber is different in each case. So this one here would be the one connected to the plenum chamber, so the box that's under positive pressure. This one is just open to atmosphere. This is the very inside of the bend, and this one here is the very outside of the bend. And if you look, in each case, it's the difference between atmospheric and the one you're measuring. So the one that's open to atmosphere here is at a level of 300 millimeters. The one at the very inside of the bend, you'll see here it's above that, but essentially this column here is being sucked up by a height difference of 10 millimeters. Okay, so this is at 310 millimeters. And it's the difference between those two that you need to work out the pressure of the fluid. The next one here is, so at the second one from the inside is actually, it's about 300 millimeters as well, so that's at the same height as the atmospheric one, the one that's open to atmosphere. So that means there's kind of a 0 gauge pressure, or it's this one is at atmospheric pressure. The next one here, and I'm going to compare that to another one that's open to atmosphere, so this one here. This is, so yeah, the third one radially outwards is this one here, and you'll see that this is below the level of the atmospheric pressure, but essentially what that means is that there's a positive pressure in this tube that's pushing down that column of liquid, and it'll be pushing up against the atmospheric pressure. So the height difference there is what you would need to measure, and there's a height difference of about maybe 12 millimeters of water, or rather, I suppose it's the height difference of 12 millimeters here. This 12 millimeters of water would be pushing down on the manifold, and that's pushing up against at the pressure that you're measuring. And this fourth one here, so this one is the one at the very outside of the bend. Again, there's a positive pressure within the tube here that's pushing down, and that's pushing against the weight of water in all the other tubes and in the reservoir. Okay, so I'll stop the fans at that and just talk a little bit more about it. Okay, so in each case there, that's an example of both a positive pressure and a negative pressure. So in the case of a positive pressure, we said we have, say, positive pressure within the tube that's pushing down, and that would be pushing against, focus here. So if you have a positive pressure in a tube, it's pushing down, and effectively what it's pushing against is it's pushing against the weight of fluid in the reservoir. So if you have a height difference here of 10 millimeters, so let's say you have a positive pressure here and it's pushed down by 10 millimeters, there's enough pressure in that tube to resist the weight of 10 millimeters of water in the reservoir. So you can work out 10 millimeters and use rho GH essentially to, rho by G by H will give you the pressure of that 10 millimeters column of water that's in the reservoir that's pushing against your positive pressure here. Okay, so rho in this case for water is 1,000 kilograms per meter cubed. G obviously is 9.81, and H there is the height of the column of fluid in meters. Okay, so that's all you need to work out the pressure there, is you need the difference in pressure between one of the tubes that's open to atmosphere, or the difference in height rather between one of the tubes that's open to atmosphere and whatever one you're measuring. Okay, and that's the fluid tube manometer in a nutshell. It's relatively simple. What you need to do is work out the difference in height in meters. Now this particular manometer is straight up and down in the air, so it's relatively easy. You can just measure that height directly off the scale. I'm just going to move over now to another manometer that's on the wind tunnel, and we'll just talk a bit about a manometer at an angle. Okay, so here's another example of a manometer. Again, you have a reservoir of fluid connected to a manifold and connected to a series, maybe 10, 20 tubes. Okay. Now, the obvious difference in this case, if we look side on at this, is that the whole manometer is laid over at an angle. But the principle of it is the exact same. You have, let's say, the pressure that you're measuring. You have a tube coming in here that's connected to whatever you're measuring. If you had a positive pressure, that would be pushing down. Positive pressure would be pushing down on a fluid here. And what's resisting that is the weight of water in the reservoir pushing back against it. So the only difference in this case is that here, let's say you're measuring, again, you're measuring against the scale on the side here to measure the level of the manometer tube and compare that to one that's open to atmosphere. The only difference here is that to measure the height for your rho GH, so that H in your rho GH is the vertical height of fluid. So effectively what it is, it's the height of the column of fluid in the reservoir. To work that out, you just need a simple bit of trigonometry. If you know the angle of the manometer, just the sine of that angle would be the height of that. So let's say, for example, if this is laid over at 30 degrees to the horizontal, so if this angle here is 30 degrees to the horizontal, a reading of 10 millimeters on the manometer scale here would actually be a vertical height up and down of 5 millimeters. Okay, so the sine of 30 degrees is a half. Okay, so a reading of 10 millimeters on the manometer would actually be a height difference of 5 millimeters. So that's the only difference. I think in that case, I think the formula is given to you for in the manual for the manometer for that. Okay, so that's the manometer. Now this manometer applies to a lot of the different experiments. So we have the wind tunnel here, has a manometer attached to it. Just looked at the flow around the bend. Flow around the bend obviously is attached to the manometer, and we had a quick look at that. There's another experiment here, uses the same manometer, that's the Venturi. So looking at the Bernoulli's effect, or Bernoulli's equation as it applies to the Venturi effect here. And then we have another experiment at the front here looking at pressure drops along a flow or along a tube. And again, that uses a manometer to measure the different pressures at different points in the system. Okay, so the manometer is used in most of the experiments here. All right, so I'll stop it at that, and I'll put up videos then of each experiment individually.